In today's lecture, we're going to start the other topic or chapter that we need to cover, and that is mass spectrometry. And as you well know, mass spectrometry, possibly, I'm going to call it, the gold standard technique, for chemical analysis. And the reason is a gold standard, is because it's a very universal technique, that can be used for not only small molecules that are drugs, but also, for big molecules, things like proteins, and polymers and so on. So it's a very versatile universal, technique that can be used for chemical analysis. And so whether you go to the environmental industry, medical diagnostics, environmental forensics, and so on, food analysis, you're gonna find a mass spectrometer, for sure, because as I said, it's a very universal technique. It's also a very good technique, because it's strong not only for qualitative analysis, and qualitative analysis, remember, refers to when I do not know exactly, the nature of my analyte and I'm trying to determine what is there. Maybe I've got a urine sample and I'm trying to see what is in the urine sample, that is qualitative analysis. Now, so mass spectrometer is an excellent technique, for qualitative analysis because it tells you what is in it, what is in the sample. But it's also a very strong technique, for quantitative, analysis because it can tell you, how much is there, of course, after you do your calibration. And so it's a very well-rounded, type of an instrumentation. And it's very, very important, for us to understand, the technicalities of mass spectrometry. Now, the reason I'm calling it mass spectrometry at a glance, is because it's a very, very wide and vast, type of, analytical technique. Essentially, even if you had, say, possibly a whole course of mass spectrometry, possibly you wouldn't be able to cover the vastness, of mass spectrometry because very, very vast. And as such, I only gonna give you a glance, on some of, the components, the overarching components of all mass spectrometers out there, and also give you the different types of, figures of merit that you need to look for as far as, how each component of mass spectrometer sort of impacts the figure of merit of mass spectrometer. And the figure of merit, remember, I'm referring to as, indicators that show the performance of the instrument, things like limits of detection, sensitivities, and all that. And remember, all those things are dependent, on the type of component, that you use. And that is the basis of all Chem 311. We are trying to study the component so that you understand the underlying mechanism and the chemistry of each, the physical chemistry of each component and how it impacts, the performance of the instrument. Now, I think it's important for me to start here in terms of, what is mass spectrometry and what types of signals, does it generate. So the mass spectrometry, essentially you're analyzing ions, so whatever gets into the mass spectrometry or spectrometer, for it to be detected, it has to be an ion. Now remember, all analytes don't exist as ions. And so if at all you have to use a mass spectrometer, you must find a way of converting, the analyte, into an ion because mass spec, is only, sensitive, to ions. It's not selective or sensitive, to anything out there that is a neutral analyte. So it has to be an ion. So of course, as I'm gonna show you in the next slide, ionization then becomes a very fundamental component, in mass spectrometers. Now, the type of output, that you get then, looks like this, so you detect an ion, and essentially what you are detecting are masses of an ion. And that's why in the x-axis here, for the output that you get in a mass spectrometer, you are detecting the mass to charge of the ion. So if at all you're doing, say the zinc 2 plus, you look at the mass, the atomic weight of the zinc, whatever it is, you can check in the periodic table, divided by the 2 plus, which is the charge of that ion. So essentially, mass spectrometer is an analytical balance. So you can think of it as an analytical balance, but it's only weighing ions relative to their mass as well as, their charge as well. And so the signal that you actually get from the instrument, is what you call a mass spectrum. It's what you call a mass spectrum. And what I have here is actually a mass spectrum, meaning, the y-axis is going to be the signal intensity, based on the detector that you use. And the x-axis, as I have said, is a mass to charge, of the ion. And of course, depending on how big the peak is, it gives you the relative abundance, of that ion in your sample. So there are many, many types of mass spectrometers out there. And maybe I'm just gonna very quickly list them here. Probably the most common types of mass spectrometers out there. There's what you, and the mass spectrometers out there actually are dependent, on what I'm gonna call the heart of a mass spectrometer, which is a mass analyzer. And so we often name mass spectrometers, based on the mass analyzers, that is inbuilt in that particular instrument. So one type of a mass spectrometer is what you refer to as a magnetic sector. The other one is a double focusing mass spectrometer. There's also the time of flight, or what you call the TOF MS. There's also what you refer to as a quadruple, the Q, often we symbolize it as QMS. There's also what you refer to as, the ion trap, AMS. There's also what you refer to as the ion cyclotron resonance. And again, as I've said, these ones are dependent, on the mass analyzer. So I've named, we often name actually the mass spectrometers based on the mass analyzer, as I have listed, but also based on the type of ionization. So often, to be more complete, mass spectrometers, are labeled based on their ionization technique and based on the mass analyzer, that is inbuilt in the instrument. So that tells you actually ionization method and the mass analyzer, sort of the two characters, that are used to label the mass spectrometers, essentially mean they are possibly the most important, components, of a mass spectrometer. So let me very quickly, look at the component of mass spectrometers, and that is all types of mass spectrometers, okay? Now, and I would like you guys, to really take note of these components. As I always say, it's very important for you to be able to sketch a block diagram, of the components that are representative of all types of instrumentations out there. So for a mass spectrometer, essentially, this is a block diagram of the components that constitute a mass spectrometer. Now, all mass spectrometers out there, of course, they have an inlet, that is the channel by which the ions, or rather the analytes, the analytes are getting into the instrument. So you've got an inlet. And then the inlet leads the analytes into what you refer to as an ionization chamber, okay? So ionization chamber is one critical component, of a mass spectrometer. Now, the other component is a mass analyzer, and I've sort of mentioned about the importance, of ionization chamber as well as the mass analyzer. Many types of mass analyzers out there and many types of ionization methods out there that we're going to talk about as well. Now, the other key component, obviously, after you have the mass analyzer, and right from the get-go, though we're going to talk a lot about, how different mass analyzers work, the purpose of a mass analyzer really, is to separate, the ions, based on their mass to charge, so that they can get to the detector, at different times, so that they can be detected, so they can be differentiated, by the detector. So the purpose of the mass analyzer is almost like a prism, when you're talking about light, so that you can, resolve, the ions based on their masses so that they can actually be detected, by the detector. So essentially, think of a mass analyzer. If you're talking about optical spectroscopy, think of it really, as a prism or a grating, or a monochromator, which is meant, to resolve. But in this case, of course, you're resolving ions, not photons. And so the other type of a component, of course, is a detector. And in almost all cases, the detectors that we use in mass spectrometers, are what you refer to as the electron multipliers. And actually, the electron multipliers are not any different, than a PMT. Remember the PMT in, when I'm talking about optical spectroscopy? Essentially, an electron multiplier is not different from a PMT. The only difference in this case is rather than a photon, you've got an electron. And then, of course, after that, you've got, the signal processor and so on, and the output, in terms of the, the computers and so on, so that you can see, your mass spectrum. Now, look at a very critical aspect, of this block diagram. The ionization chamber, in most cases, not in all cases, in most cases, the mass analyzer, in all cases, and you've got, the detector, in all cases, they are actually in a vacuum. So in essence, all mass spectrometers, you need a vacuum, so that, of course, the mass analyzer is inside a very low pressure, region. So it's in a vacuum. It's in a vacuum. Of course, you can see why. Ions are very, very lightweight, so essentially you don't want them to be in a very unstable environment with air and so on, because they become very, very unstable. So for you to be able to control an ion, you really want it, in a evacuated, in a vacuum environment. So let me very quickly, talk about how each of the mass analyzers work, because it's very important, for you to understand, the underlying basis, of each, how each instrument or component, as far as the mass analyzer is concerned, work. So you got this thing called the magnetic sector. And as the name suggests, magnetic sector mass analyzer is based on the premise that if at all I've got an ion, okay, and I expose an ion, to a magnetic field, so sometimes people call it B. Most people, crystal magnetic fields with the symbol B. So if you expose ions, in a magnetic field, what typically happens is that they deflect. Essentially, they change direction, okay? And they change direction, based on their masses, their mass to charge. And so based on that, then, you can apply a magnetic field. And if at all the mass to charge, of that particular ion is quite large, it won't be deflected as much. But if at all it's lighter, then it's going to be deflected more. And so based on that, you'll be able to resolve, the masses or the ions, based on their mass to charge because of their preferential change of direction, based on based on the magnetic field, that you impact, on the system. Again, as I said, if they are fairly light, type of ions, then they're gonna be deflected a lot more. If at all they are fairly heavy, then they would be deflected, as much. Okay. And so based on that, you do the resolution. And clearly, as you can see in this case, you've got a gas sample, which is a gas sample maybe coming from the GC. It goes through the ionization chamber, and we're going to talk about different ionization chambers out there. And so it becomes, an ion. Maybe initially it was just a neutral analyte. And then, when it gets to the magnetic field, it gets deflected. And because it gets deflected, now it can be collected, by the detector. And at all there are many, many ions out there, then they can actually be measured, because they will reach the detector, sort of different directions. Now, magnetic sector, is probably the oldest, mass spectrometers out there. So when we're developing the mass spectrometer, this is the oldest, mass spectrometer. Now, its resolution is also very, very good. It's got a very high resolution. And of course, the resolution is dependent, on the type of magnet, that you're using, the strength of the magnet, and so on. Now, one disadvantage, of the magnetic sector instrument, is it is very expensive. Sometimes, creating some of these magnets, just like an NMR, they tend to be fairly expensive, as well. And so magnetic sector instruments are generally fairly expensive, and they are bulky, as well. And so that's one disadvantage of these instrument, that has got very high resolution, but they tend to be fairly bulky and not fairly easy to miniaturize. But its resolution is perfect. So for a benchtop instrument, or rather for a localized instrument, that needs to be in a room, and you have the money, magnetic sector instruments are very good because of their very high resolution. Now, another type of mass spectrometer, again based on the mass analyzers, is what you refer to as a double focusing mass spectrometers. And the double focusing mass spectrometers actually comprises a magnetic sector, based on, the deflection of ions, when you expose them to a magnetic field. But remember, you're only taking care of, the deflection of the ions just by changing, sort of, their direction. Now, to improve the instrument, people realize if you put an ion, such as the M plus, and expose it actually, to an electric field, its energy, sort of is dependent, on the electric field, that you expose it to. And so equally, you'll be able to stabilize it, based on, the type of energy, electric field, that you expose it to. So in this case, you expose it to an electric field. And, based on that, you can actually determine equal, and then after that, you expose it to a magnetic field. And you've got sort of two mass analyzers that you're combining together so that you can improve, the resolution. So the reason actually why sometimes people call it, the double focusing, is because of the fact that, you are doubling, you're sort of using two different types of mass analyzers, the electric field, or what they're calling it here, the electrostatic analyzer. Sometimes actually people call it the reflectron, this type of mass analyzer, where you've got an electric field, people call it a reflectron. And the idea, as I suggested, is, if at all you've got an ion, of course, all ions tend to be mobile, so they are moving all over the place, and you expose it, to So it means that it has a kinetic energy, it's mobile, and you expose it, to an electric field. Now, if at all you've got ions that have got less kinetic energies, they're gonna be deflected less, by the electric field. And those ones, of course, with high kinetic energy, they're gonna be deflected, more and so on. And so you'll be able to focus, the ions based on their electric field based on their electric field. Now, double focusing mass spectrometers, essentially, again, they've got fairly good resolution, and they're fairly expensive, as well, and they're bulky, as well. Okay. Maybe just to emphasize this thing again, with the electrostatic analyzer, as I said, most of the ions come in, with differential kinetic energies. And so they are mobile. And so sometimes, the electrostatic analyzer, which is a reflectron or a mirror, an ion mirror, which comprises, just a sheet, with a voltage applied to it. If at all the kinetic energy, of the ion, is very, very large, and they're very, very different. If at all you expose it, sort of, to an electrostatic analyzer, you're able, to focus and dampen, the different, translational energies, that the analytes start with. And that's why they call it, focusing, the ions, based on their energy. So take note of that. The electrostatic analyzer, again, is meant, to focus the ions that are coming in, and they've got differential translational energies. And you want to make sure that the ions are starting sort of with the same translational energy as they get to the mass analyzer. You can use a reflectron on electrostatic analyzer which deflects equally the ions based on their translational energies. So again, fairly good instrument, but bulky. Bulky and high resolution, and expensive as well. Now, the other type of mass analyzer is what you refer to as a time of flight, the time of flight mass analyzers. So the time of flight mass analyzers is fairly easy, to understand. Now, first, of course, you've got, the analyte, inlet there, and it gets through an ionization chamber. And we can see the ionization chamber in this case is what they refer to as the electron impact, which is just a filament, a bulb, generating electrons, and then you've got, the analyte M, and the electrons, hit the M, causing ionization to happen, such that, when they are getting out of the filament, essentially, they are in an ion form. Now, with the time of flight, you expose these ions, into a tube, that is a very, very low vacuum. And some people call it, just a flight tube. So essentially, you can think of it, as a relay, when you get these ions in a tube, and all what they need really to do is to run through the tube, and based on their masses, the ones that are very, very heavy, they're gonna run slower. The ones that are lighter, the ones that are lighter, they're gonna run faster, and so they're gonna end up in the detector, at different times. And so that's very easy to understand, the time of flight. In fact, usually the tube, can be about 2 meters long. And so the ions, just accelerate in a relay, through the tube. And as I said, the heavier ions, reach the detector, last. whereas the lighter ions, reach the detector earlier, and that way you are able to resolve, the analytes. Again, fairly easy, to understand. Now take note of this. Now the ions, need equally to be pulled, to the detector, otherwise they're gonna fall off, somewhere, along the flight tube. So how do you move the ions, to the detector? So typically, you just use a pair of electrodes, an electrode here. Assume the ion is positively charged. You just need to apply a negatively charged of a certain electric field, maybe minus, 2000, V, or even 2000 V is very, very commonly used. And then now you can pull, sort of, the positively charged ions, across the tube. And I said, the heavier ones, are gonna drag, the lighter ones are gonna run faster and reach the detector earlier. So fairly easy, to understand. Now, just as I said, sometimes you may have this thing called an electrostatic mirror, being integrated, in the time of flight. Okay, think about it. If at all you've got, say, a GC here, and the GC is what is being used for the separation. The analytes, are going through the source, which is the ionization chamber, coming from the GC. It means, that these analytes, have got very different translational energies. They've got very different kinetic energies. They are already mobile already. Now, meaning, you want to make sure that before they get to the time of flight tube, essentially the starting has to be the same. So it's almost again like you're in a relay. You essentially want everyone, to start at the same time. You don't want some people, to start running before the gun, the start gun is on. So similarly, what people do is to integrate this reflection, which again is an electrostatic mirror, is an electrostatic analyzer, so to say, where these analytes, that are mobile, they get deflected, based on, based on their energy, so essentially you apply, it's a set of electrodes really, and then you apply voltages on these electrodes. And so depending on the translation or energy, of one ion, it gets deflected or penetrates, the reflection, based on its energy, and then it's dampened, meaning it's brought to a stop. And after it's brought to a stop, then now it can be accelerated, into the time of flight when all of them have been dampened, by the reflection or the electrostatic, analyzer. So it's very similar to what I talked about before, the double focusing. In this case, the reflectron is used, to dampen the ion so that all of them have got the same kinetic energies by the time they are starting the race on the time of flight. So reflectrons, are integrated in most of the time of flight mass analyzers. Now, there are many advantages of time of flight, such as, very high resolution. You can see that, very high resolution. And by the way, what I mean by resolution, it's calculated, as m divided by the delta m. Meaning, if at all I've got m average, that is. Meaning, if at all I've got, two ions, maybe 200 and 201 atomic mass units, can I separate them? So essentially, I just need to take 201, 200, I get an average of that. And then the delta m would be the difference between the two, and the ratio is what I'm referring to as the resolution. Okay, so very similar to what we did, with the optical spectroscopy. So they have good resolution. Now, another very good thing about the time of flight is that, they can be used to detect huge molecules, large molecules, large molecules. You can see their upper mass limit, can go all the way, to 1 million atomic mass unit, meaning they're very good, for analysis of polymers. And as you can see, again, they're used, for biomolecular applications. You're gonna see, when you're analyzing proteins and so on, time of flight, is a way to go actually. Now, some of the disadvantages, are things like it's fairly expensive. You're talking of $200,000, $300,000. Now, sensitivity limitations as well. And of course, you're using high voltages, as well, and tends to be a fairly bulky instrument as well. So fairly bulky instrument as well. Now, the other type of mass analyzer out there, and I would say the most common because it's fairly small, you can miniaturize it. So this one is is fairly small. Is what you refer to as a quadruple, the quadruple mass analyzer. And the quadruple mass analyzer, which sometimes people call a mass filter, is based on using 4 sets of iron rods that you superimpose a radio frequency field, as well as, a direct current field. So you can see again, they are all based on electrostatic analyzers, so to say. Meaning, if at all I've got an ion and I expose it into an environment, of an electric field, it gets deflected. It gets deflected. So the way it works is the following. I've got, an ion source here, so the analyte is going through the ion source. It gets ionized, okay? And of course, there are many ions as well. And then I apply a radio frequency field, across, these electrodes or these ion pores. And I apply equally direct current, across. I superimpose, a direct current, across, the iron rod as well. Now, depending on the amount of the DC and the RF voltages, that I apply, my ions, can be either stable or unstable. So you see, I'm trying to deflect it, based on the energy, that I'm applying using, the radio frequency and the direct current field. So essentially, I'm trying to make either the ion stable, so that it goes all the way to the detector. If it is unstable, then it hits those rods and it gets annihilated. It gets destroyed, such that it doesn't, end up in the detector. So the idea is to apply a different range of radio frequency and the direct current, so that some of the ions get unstable. They do not reach the detector, and others, actually get to reach the detector. And based on that, I do what I'm referring to as scanning. So you can see I'm increasing, the DC potential, to make some of the ions stable, and they reach the detector, and I keep increasing it or changing it, such that all the ions, reach the detector at some point. All right, so I'm trying to deflect it so that they keep reaching the detector, at different times. Again, based on the DC voltage and the radio frequency voltage that I'm applying. And again, their deflection is going to be based on the masses, of the ions. So again, the masses of the ions determine, if they reach, at what point rather, they reach the detector, based on the push and shove coming from the radio frequency and the DC potential. So again, as I said, one huge advantage of the quadruple is the fact that, it's fairly small. You can easily miniaturize it, and the fact that actually the instrument typically is not very expensive. Somewhere around, $150,000, you can get a quadruple, mass analyzer. Now, one disadvantage, of the quadruple mass analyzer is that its resolution is poorer. It doesn't have a very high resolution. And also the mass range is very limited. So you'd find quadruples are typically used, for smaller molecules. Okay. Now, for example, those of you who have used our GCMS system, and some of you have, you're gonna find, the quadruple, is a mass analyzer, in those instruments. Now, the other type of mass analyzer is what you refer to as a quadruple ion trap, mass analyzer. And as you can see, essentially, you see the importance really of electrochemistry, because we use electrodes really to manage the trajectory, of these ions. So the ion trap, essentially comprises, a container made of electrodes. So you've got, the end cap, so you've got, the end cap electrodes, and then you've got, the ring, electrodes as well. And then you've got, the ions, getting into this trap, which is just a container. And then you apply, a DC voltage slash, a radio frequency voltage inside, this container. And as I said, the ions, gets deflected at different angles, based on, their weight, and of course, based on the force or the energy, that you're applying. And so based on that, you can have some of the ions being extruded, coming out, from the trap at different times, based on their masses, so you're trying, to create instability inside the trap, so that the ions, jump out, and they're gonna jump out, based on the energy, that you're applying, based on the DC and the RF voltage, of the electrodes. And of course, the jumping out, of the ions is gonna be based on its weight as well. Meaning, if at all I've got a very light ion and I apply a DC voltage, its trajectory shifts very, very quickly. And so I can actually extrude, or, have that ion, escape, the trap, fairly quickly, and then it ends up, into the detector. So you can see how interesting, it is. But it's based exactly on the same premises, of using, different types of electrodes, but in different architectures as well. You can see it's very, very similar, to a quadruple and so on. Very, very similar, even to a time of flight, to some extent. You're just using voltages, to play, with the ions. So hopefully, these ones sort of explains it even better, where you've got the ions coming through, they get ionized using different methods, and I'm going to talk about the different methods of ionization. And then they get into this trap, the ion trap, which, as I said, you've got the ring electrodes, and then you've got the end cap electrodes. You're applying DC slash RF voltages, and the ions get deflected and they escape the trap, based on their mass to charge, and they get detected, using an electron multiplier, and then you've got a mass spectrum, in the end. So some advantages, of the ion trap, is the fact that you're trapping the ion, meaning you can actually do a lot of chemistry, inside the trap. Okay, so you don't lose the ions per se, other than those ones you extrude. So some people do what they refer to as the tandem MS, where you trap the ion, and then you fragment, that ion inside the trap, and then you analyze the type of ions that you are generating. You can even fragment, these so-called daughter ion. People call this a parent ion. You can fragment the daughter ion and look at the different types of components or ions that come out of it. And so based on that, you can actually determine what type of analyte it was, depending on the fragments, that are coming out of it. That's why I say it's a very good qualitative, actually, qualitative technique. If I do not know what is in it, essentially I can keep chopping the parent, molecule or ion, to look at the daughter ions, and then I can piece it together, to determine what was actually present. So it's a very good instrument for qualitative analysis if I do not know what is in it. So some people say, you can do MS up to the 6, meaning I take a daughter ion, M plus, I fragment it maybe to N plus, I fragment these again maybe to S plus, and so on, up to MS, to the 6. But of course, with each fragmentation, you also lose sensitivity as well. So some of the advantages, of these instruments, of course, the fact that you can do tandem mass spectrometer, and maybe some disadvantages is that, of course, the resolution tends to be poorer. The resolution is poorer, and you cannot use it for very big molecules as well. Really, it's a quadruple. So the same disadvantages of a quadruple, applies, to the ion trap as well. Now, the ion trap, typically requires, a bit of helium. So, in fact, when I'm talking about doing tandem MS, essentially helium is what people use, to collide with the ion, so that you can get, the daughter ions as well. So typically, you often need helium in when you're using, when you're trying to do the trapping, when you're trying to do the trapping, of the ions. And essentially, you can see that if the helium is on, you tend to get very, very good data, good resolution. When the helium is off, you don't get very good, type of results. So the next chapter, or rather the next talk, we're gonna talk about now the different types of ionization.